Swayam Prabha. Digital India. Educated India.
Welcome to Introduction to Machine Learning. From this lecture onward, for the next few lectures we will be talking about unsupervised machine learning. Before this we were talking about supervised learning, where the target values for each sample were given. Now we will not have the target values for each sample, yet we would want to make some representation, learn some representation of the given sample so that those representations are useful in some sense. So let's look at those criteria. The first one that we will talk about is clustering, and let's dive into it. So the objectives of this module would be to list applications of clustering, obviously understand what is clustering first, and then write the objectives and algorithms for certain ways of doing clustering, okay, and then list the methods to assess goodness of clustering. Okay, so first of all let's talk about what is the objective of clustering. So let's say we are just given a bunch of sample points without any labels, without any target values. So let's take an example. So let's say you have x1 and x2 dimensions. So this is x1 and this is x2, and within that all we are given are several sample points. And what we want to do is we want to find out whether these sample points belong to natural groups of some sorts, natural subsets of some sort. So what you can see from here is probably that it looks like these points belong to one group, right, and these points belong to another group, and we cannot say about the 3 points that are lying outside these two groups. So what is the criteria for defining these groups? What are some algorithms to find these groups? That is basically what we will be looking at. And why is it useful? There are several reasons why it could be useful. There are different applications of clustering. Sometimes we just want to find natural groups. So imagine you have a company and you want to have marketing forces that go after different market segments using different strategies. There are certain market segments where you want to play the numbers game with more efficient targeting of each customer. Then there are certain segments where each customer brings you more revenue, so you want to give them specialized treatment and so forth. So this market segmentation is a very classic exercise in business, where we don't know a priori that what segment to assign to each customer. We just have customers and we have some data features about them. For example, we may know the revenue per customer, we may know the profit per customer, we may know the volume, we may know how much time they spend in our store, we may know how much time, how many times they come to our store and so forth. So with all these different variables that we know about the customer, we may want to segment them into some natural groups and then form sales teams or marketing teams that go after individual segments, and their strategies would be very tailored to that segment as opposed to a generic customer. So finding these natural groups becomes a very important exercise in that case. Another example could be to reduce the data and deal with only a typical sample from that particular subset of data. So let's take the example of cancer. So let's say we have different patients. We have patient 1, patient 2, patient 3, and so forth, and patient N. and then on the other hand for each patient we have gene 1, gene 2 up to gene D. Okay. So we have so many different genes and patients, and these all have some values. So in some sense we have a matrix just like the data matrices that we have been talking about, but we don't have any target value associated with every row of the matrix. So it's an unsupervised problem. What we would like to do is to say that these patients look alike and they will benefit from one type of therapy versus some other set of patients that look alike in their gene expression and they would benefit from another type of therapy. So the targeted therapies for subtypes of cancer could be based on clustering of gene expression. On the other hand, we can also cluster genes itself. So we can even cluster genes that these genes appear to be switched on or off together, whereas these genes appear to be switched on or off together. So we could cluster in both dimensions, both the sample dimension as well as the gene dimension, or the patient dimension as well as the gene dimension, and you will see in some biological literature you will see a two-way clustering where both genes and patients are clustered. So it's quite a useful exercise in those fields where we are doing knowledge discovery, right. So in supervised machine learning we knew the target values for every sample, and we were trying to fit a model that will predict the target value for test samples. Here we want to discover natural groups or natural ways of representing data given the raw data. Another example of an application would be to find outliers. So if you have different samples that look alike and another set of samples that look alike, and then you have another sample that is not like any of these, then if we do the clustering we may find that this is one cluster, this is another cluster, and this is either a cluster or a small cluster or an outlier on its own, and it actually belongs to some, it is an outlier as far as most of the data is concerned. So an example would be that if you are looking at cars, right, and you are looking at their size, their power, their speed and their doors and so forth, it's possible that most of the two-door cars cluster in a certain speed and acceleration dimension also, whereas the four-door cars are in another cluster, whereas there might be only one or two models of three-door cars which are outliers in that case. So it also basically goes down to modeling the density or probability density of the data, the joint probability density across all the variables of the data. When you are looking at this joint probability density, the contours of density could be multimodal, and each mode itself is representative of one cluster, and wherever you see low density regions and one or two points there, those could be the outliers. So there is a good connection between density estimation and clustering. So we will look at density estimation also later in the course, but now let us start with clustering. So clustering is actually not an easy problem because it is an unsupervised problem. Let's take an example. So let's say we have a bunch of data points. So let's say we have these data points. So if someone asks you how many clusters are there in this set of samples, then it's hard to say whether these are 4 clusters or 3 clusters or 2 clusters. All of these could be right answers depending on what you are looking for. If you are looking to have only a few clusters, then probably the 2 clusters that you see are these 2. If you are looking to find a more number of clusters, then probably you have these 4 clusters, right? And it's also possible there's an intermediate where where these 2 clusters are actually one cluster, but the other 2 clusters are 2 separate clusters, so we have 3 clusters. Another possibility could be that we do such a fine job of clustering, such fine cutting of the clusters, that each point becomes one cluster. So in general, you can, if you have n samples, you can have n clusters, or you can have one cluster. So you can have anywhere between 1 to n clusters. Now which of those are good, we don't know, right? So that there is no one answer for every problem, but depending on what prior assumptions we have about the data, what prior assumptions we have about what is a good cluster, there are different, you can get different answers. Another example could be that, let's take another set of samples. So let's say now we have points that form a line, right, and then we have another set of points that form a line which is close to the same line, right. So in this case there is a possibility that you might want to consider this to be one cluster and this to be another cluster, whereas it's also possible that you may want to consider these set of points as one cluster and these set of points as another cluster. So the correct answer is not obvious, and it all depends on what is our prior assumption and what is our application in mind, what is our utility in mind when we are doing clusters. But keep in mind that if you have n points, you can have anywhere from 1 to n clusters. Let's start with the most popular clustering algorithm, which is the k-means clustering algorithm. Basically the idea of this algorithm is that we will take all the n points that we have and we will do a hard partitioning into one of k clusters, and this k is something that is fixed. We will assume that we know k, so k is your hyperparameter, it's a hyperparameter. So this is something that you choose before you begin the algorithm, and once we have chosen the algorithm, the objective of the algorithm is to minimize the sum of squared distance from the cluster center. So there are couple of words to unpack here. So first of all, what is a cluster center, right, and then sum of squared distances from each point's own cluster center. So what I mean by that is that, let's say you have points xi where I ranges from 1 to n, and then you have clusters small k ranging from 1 to capital K, okay. So basically what we will say is that for each point xi, it belongs to some cluster, okay, it belongs to some cluster ck, okay, and if xi belongs to ck, this implies that xi does not belong to cj where j is not equal to k. So what that means is there is hard partitioning, the cluster, the point cannot belong to more than one cluster, and the point will belong to at least exactly one cluster, let's put it that way. So xi will belong to exactly one cluster. So let's take the set of points, okay, sk. Sk is the set of points or set of samples belonging to ck. Okay, so this is all the points that belong to the cluster ck. So what we want to do is we want to minimize, okay, minimize by changing ck, minimize over ck the sum of squared distances. So we will have I and sum over k, small k, okay, and we will have an indicator function, and this indicator function is xi belongs to ck. So only then this is 1, otherwise it is 0, and what we will do is we will take the difference of xi minus mu k squared. What is mu k? Mu k is the centroid, okay. So mu k is the centroid is equal to 1 over ck, all the number of points within ck, and we will basically take this xi indicator function, xi belongs to ck, and we will take xi, okay. So if we take all the points and we that belong to one cluster, and we take their average location, that is the centroid. Okay. So this is your centroid, and this is the objective. Now whether it meets this objective or not is a different question. It tries to meet the objective, but it may not always meet the objective. It may not always find locations in the space where the clustered centers minimize the distance from their respective points. So let's look at it in a more visual way, and that will help us define how we are trying to meet this objective. So let's say you have a bunch of samples that are given. Okay, so we have some samples that are closer to each other here, and then we have another set of samples that are closer to each other here. So how will we find these cluster centers that are that minimize the sum of square distances from their own points? So initially we would not know any of these, right? We would not know what these cluster centers are. So let's say we randomly initialize, or let's say we end up at some point deciding two cluster centers, and let's say k is equal to 2. So somehow we figured out that a good k is 2. We did not select k is equal to 3, we did not select k is equal to 4. Somehow we started with k is equal to 2, and let's say one of the points is here, okay, and the other point is here. Alright. So the first thing that we will do is we will find out which points belong to which cluster. So what we will do is, if you look at these 2 points and I join them with a line, and this line, on this line I compute a perpendicular bisector. Okay. So let's say that perpendicular bisector is here. So let me draw this line bold. So this line defines, on one side of the line everything is closer to one centroid, one cluster center, and on everything on the other side every point is closer to the other centroid, right. So basically this defines the membership of all the points. So these are all belonging to, now let's take a different color. So here all these points, they belong to the square centroid, because they are closer to the square centroid as opposed to the triangular centroid. On the other hand, so here let me expand this, actually it is going to include some other points also, it is going to include these points also. Whereas if I look at all the points that are circled by red, right, they belong to the triangular centroid, and because they are now closer to the triangular centroid as opposed to the square centroid. So this defines the membership of each sample point. So each sample point either has the membership to cluster 1 or to cluster 2. Alright. So because it has one of those two memberships, now I can recompute the centroids for cluster 1 and the centroid for cluster 2. So when I recompute, right, so this centroid will shift towards the center of where majority of the points are, and it will not be exactly there because of this outlier. We have an outlier here, but it will shift closer to this point, whereas the square centroid will shift closer to these other points, but it will have these two outliers that are basically changing which are preventing it from being exactly at that center. However, once these are shifted, right, then my partitioning of the cluster changes. So this partitioning of this cluster changes, and my next blue line will be something like this. Okay, the next blue line that basically partitions the points into two different cluster centers will change, and now it looks more natural. The division of the points between cluster 1 and cluster 2 looks more natural, and because of that in the next iteration I might be able to find the exact centroid of the two natural clusters that I can see on the screen. So basically my line will shift. Okay. So that is the visualization, and in the end basically the clusters that I will get will most likely look like this, and it will look like this, sorry. Okay. So if we want to write this more formally, so we will have some iterations, right. So basically we will have an iteration loop, and its terminating condition would be when there is until little change in centroid locations, until change in centroid locations is less than some tolerance epsilon. Okay, so this will be the iteration loop. Within the iteration loop, what we will do is, so before the iteration loop, we will randomly initialize centroids. Okay. Then within the iteration loop, what we will do is number one, compute membership of each point. So what is membership? Basically we will look at the difference between xi and all cj, so or all mu j's, right. Let's call this mu1, let's call this mu2. Okay. So we will compute the distance between, so we will find basically arg min over j of xi minus mu j, or let's just call it distance d of xi comma mu j for each I. Okay. So whichever j minimizes that is the cluster to which the point xi belongs. Alright, and then we will do one more thing, we will recompute mu j for all j. Okay, so we will recompute and we will reinitialize, we will find the cluster centers again. So now this will be based on the centroid computation. How will number 1 work? So this is number 1. How will number 2 work? Number 2 is that mu j is equal to 1 over cj membership, right, and sum of xi if xi belongs to cj. Alright, so it's just basically a centroid computation. So that is the entire, not just a single iteration, but the entire algorithm for k-means. Alright, so that basically tells us the entire k-means algorithm. So couple of things to note here about this algorithm is that when we go to the next slide, that first of all we need to think about how will these points be initialized. One way is to choose random points, random cluster centers in the first iteration, before the first iteration, and then just proceed from there. So one possibility is random initialization, which I talked about in the previous slide. Okay. The other possibility is that each cluster center should be very far away from each other. So this would be pick furthest points, and by furthest points I mean these are subsets of the training points that or the sample points themselves that are given to us. So a rough or a greedy method would be pick any point, pick first point randomly, okay, pick next point that is furthest from the previously picked points. Okay. So these are some different ways of doing the initialization. The challenge comes when you have, when the number of dimensions is very large, then picking the furthest point becomes a little bit of an issue, because we are doing that distance measurement using Euclidean distance, and Euclidean distance sometimes is not a good measure of nearness or for or how far points are in high dimensional spaces. But sometimes we don't have anything better than Euclidean distance, so usually we just use Euclidean distance. Later in the lecture I will also talk about how the transformation of variables can change how clustering is done. Okay. So complete k-means algorithm, we already looked at the entire algorithm, but let's look at the stopping criteria of the k-means algorithm. Right. So first of all, know that the k-means algorithm will not update to an will never have an update where the average sum of squared distances is more than the previous iteration. That will never happen, right. So we can actually prove it whenever we are computing a centroid of a given set of points. In the next iteration, because the membership itself is based on minimum distance, it will never increase the distance. So that is the outline of the proof. So whenever we, so the second part is that because we are assigning a membership to each point, there are only finite number of ways in which we can assign that membership. To be more specific, if we have n points, each point can have one of k memberships, so we will have k to the power n different total memberships that we can have. Okay, so k is the number of clusters and n is the number of data points. So because the membership, if the membership doesn't change, the criteria of k-means clustering will not change. So it will always stop within a finite number of iterations, okay, or within a finite number of iterations you will have no change in the cluster assignments. Consequently, you will have no change in the average distance of points from their nearest centroid. Okay. Now, however, this k to the power n can be a very large number, so we still stop the clustering at a point where we have no appreciable change in the sum of squared distances of each point from their cluster center. So that could be an arbitrary stopping criteria based on some tolerance epsilon. The last thing to note is that once we are running this k-means algorithm, we are not guaranteed to find the absolute minimum sum of square distance, not guaranteed to be optimal. Right. So this algorithm is only a greedy algorithm, and it is not proven that it will always find you the minimum distances, sum of square distances. Okay, so these are some of the things to keep in mind. One thing that we don't know about these points is that how to choose k. So these issues remain, how to choose k, and second thing is that why should we do hard clustered assignment, why can't we do soft cluster assignment. That means that each point has can belong to more than one cluster, maybe it belongs more to one cluster than to another cluster. So this basically takes us to another type of clustering, which is fuzzy C-means clustering, very similar to K-means clustering, except that the membership criteria is not going to be hard. Right. So if we want to visualize this in 2 dimensions, what we will have is that if we have a bunch of points here and we have a bunch of points here, the clustering membership will basically give us a hard boundary. Okay, it will give us a hard boundary like this between the two clusters, right. How if k is equal to 2, if k is equal to 3, perhaps it will give us another hard boundary like this. Whereas in fuzzy C means, basically you can think of some contours that are sitting here, where the center of the contour is highest membership for that cluster, but then there is another set of contours that are sitting here, and each point can belong to more than one cluster. The sum of its membership to different clusters will be 1, however it can have fractional membership to any cluster, and that seems more useful to us initially, at least when we do not want to do the hard assignment, and it sometimes leads to breaking of escaping from the local minimas in the clustering objective. So basically what we do is we want to minimize a weighted sum of square distance as opposed to sum of square distance. In k means it was sum of square distance, here we are doing weighted sum of square distance, where the weight is some weight wij to the power m, okay, and this m is greater than equal to 1. Alright. So this m controls the fuzziness factor. M is equal to 1 implies we will have something like k means clustering, hard thresholding. Okay. So you can think of your clustering membership as, let's say you have a bunch of points here in one dimension, another bunch of points here in another dimension. Hard clustering will the points will either be a member or not be a member. Let's change the color. In hard thresholding, the points will either be a member or not be a member. This is x1, this is membership. Okay. In soft fuzzy C means, what we will have is soft membership, where the membership will be slightly less than 1 and then it will be slightly above 0 for the points that are quote unquote outside the cluster. So they are never truly outside the cluster, they just are not as strongly a part of this cluster as they are a part of the other cluster. So now what is that weighted membership function? A popular choice of that is that we take the distance of the ith point from the jth cluster center, again it is a centroid, alright, and we take its ratio with that of another cluster and we sum it over all clusters and raise it to the power 2 divided by m minus 1. Okay, and this whole thing is in reciprocal, it is raised to the power minus 1. So the intuition behind this is that, let's say if m is equal to 1, then this then basically what we are doing is we are raising this term to the power infinity. When we raise it to the power infinity, it becomes the weight becomes sort of like an L infinity norm, and it will only be applicable to those points where the point is closest to the cluster center. So that will it's like a reciprocal of the L infinity norm, L infinity norm of the reciprocal of the distance, of the 1 over distance. So it will take the one where the distance is the minimum and it will assign all the weight to that, and it will not assign weight to the other clusters, and then it will become sum of square distances. Here on the other hand, when m is greater than 1, then we have more fuzziness, and we can even do some sort of annealing where we start with a large m and we slowly tune m and make it smaller, make it closer and closer to 1 until we get hard cluster assignments. To visualize this, let's look at this image and look at all the pixels in the image. These pixels are dark, these pixels are light, and light pixels have high value, high intensity value like here, and dark pixels have low intensity values like here. So let's say we want to segment the objects in the image based on their intensity value. We want the dark flower to be part of one segment, the light flower to be part of another segment, and the intermediate grass blades of grass here to be part of a third cluster. So let's say we start with C is equal to, or the number of clusters is equal to 3, and once we have done the cluster, the entire clustering algorithm, where it's very similar to k-means, except that what we will do is we will recompute the distances based on we will recompute the membership to be based on we will recompute the centroids based on weighted sum of the points that are in the cluster. And what we see is that once we do the clustering, we have 3 different clusters: the red cluster, the blue cluster, and the green cluster. And the red cluster has the darkest points, the blue cluster has the brightest points, and the green cluster has intermediate points. And the membership function looks like the following: it's never truly 1, it's 1 for only like a certain set of points, and this is for a particular m value, and then it fuzzily drops off. Similarly, it is high for intermediate points for the second cluster, and it is high for brighter points for the third cluster, but it never truly is 1 for more than a single intensity value. So with both k means and c means, we have a certain prior assumption over clusters, and that assumption is that these are equal sized isotropic hyperspheres. What does that mean? It just means that if we have 2 dimensions, we assume that clusters are balls of equal size, circles of equal size. In 3 dimensions they are balls of equal size, and in n dimensions they are equal sized hyperspheres. And what I mean by isotropic is that the distance measurement in any direction is the same. Okay. So this is the assumption of k means and fuzzy c means. In both this criteria, you cannot have one small ball and one large ball. This does not happen, and neither does this happen that the balls are squished in certain directions. Neither of these two happens. Okay, so that's a drawback, because not always we would want all the points to be lying within a hypersphere, and that too of an equal size, right. Sometimes you can have points that are more spread out in one cluster, and now some of these points will start to belong to the other cluster with both k means and fuzzy c means. So why is it so that we have this prior? The prior comes because of this criteria that we are using, xi minus cj, and we are taking its Euclidean distance squared, and we are trying to minimize this. Okay, we are minimizing this over sum of all I and j for all the I points that belong to j, or a weighted sum in the fuzzy c means, where we don't look at membership as a 0 1 function, but as a some value between 0 and 1. So the membership will be between 0 and 1. So just to recap, for fuzzy c means, whatever weight that we will get, so if we get wij, the membership will be wij and then sum over all wij, or here it will be k rather, we will use a different index, all ik for summed over all k. So this will be the membership of ith point to the jth cluster. But the same assumption that these hyperspheres are equal size also applies to fuzzy c means, because ultimately it is the centroid computation is based on Euclidean distance, where the Euclidean distance thus is isotropic in every direction, and the membership is it behaves similarly for any point in space. The Euclidean distance behaves same from this center as well as this center, but we may not always want it to be like that. We may not always want cluster membership to be like that. So there are an alternative set of approaches called density based clustering. An example of to motivate that would be the following. If you look at the blue points and the green points on the screen, you can see that they don't form hyperspheres of equal size, they don't form circles of equal size. In fact, one of the set of points is not even a cluster, is not even a circle, it is actually in this C shaped, whereas let's change the color here. So this almost looks like a circle, but this doesn't look like a circle, it looks like a C shape looking in the other direction, or a boomerang shape. Yet it seems obvious, at least for some applications, that these are two separate clusters and their shapes are quite different, their sizes or spatial extents are quite different. So this is where density based clustering is useful. Basically what we mean by density based clustering is probability density of points. So we have this x1 space and we have this x2 space, and we have some joint distribution of x1 and x2 from which these points are sampled. So we have p of x1 x2, right, but we don't know p of x1 x2 exactly, we just have samples from that space which are the dots that you see on the screen. Now based on these dots, can we say that this density is multimodal? So if we just look at one dimension, if we are looking at just x1 dimension, we are looking at the probability, so this would be a unimodal distribution, whereas this would be a multimodal distribution, right. So in this multimodal distribution, it is obvious that, it seems obvious that we have two clusters, right. We have a cluster of points that belong to this mode, and we have another cluster of points that belong to the other mode, right. So similarly in two dimensions we have two modes here, one is the green mode and the other is the blue mode that you see on the screen, and they belong to two different clusters. So what defines a cluster? Hopefully if we have enough points from sampled from the probability distribution, we will have a high density core of arbitrary shapes. So this is the dark portion that you see here, that is the core portion, okay. So here the equivalence would be like some sort of a tolerance around the mode, okay. So around the mode, if we look at a small region, that's where we will see a lot of points that are neighbors of each other if we have sampled enough points. So that is our core region, right, and outside the core region there is a little bit of a small gap where we will have slightly lower density, and that is this fuzzy region that you see around that. So we have high density region and medium density peripheries around it, okay. So this high density combined with medium density tells you where the cluster's core is and where it is ending, and then we have these low density regions. So these are low density regions, this is medium density region, let's use a different color. So high density core is here, the medium density is here, and low density is here, right. So this high density core region is here, the medium density periphery is here, and the low density regions are here, okay. So anything that is outside of that periphery is a low density region, and the points there we do not necessarily want it to belong to any cluster, we want them to remain as outliers. So how do we model this density? There are different ways of modeling density, we will get into some more well defined ways of modeling densities later, but let us now look at a more heuristic method which is used by this clustering algorithm called DB scan, database scan, where we are trying to model these densities using these three key concepts. So to use those three concepts, we will use two hyperparameters. One is minimum number of points m and a tolerance of distance epsilon, okay. So first, based on these two hyperparameters, we will define three types of points. We have core points, these are points in the high density region. So this is high density, okay. These are points where any point, if we pick any point, let us use a different color so that it is visible. So if you look at a core point, it has, so let's say our min distance is 2, okay, our min number of points is 2, okay. It has at least 2 points that are within a radius of epsilon. So at each point I will draw a radius of epsilon at each point. So at each point I am drawing a radius of epsilon. Within that, if I find m points, then it is a core point, okay. So that means it is from the high density region. So we have to decide what is epsilon. Epsilon is this radius is epsilon. all these radii are epsilon. Okay. So if I find m points within the radius epsilon, then it is a core point, it is from a high density region. On the other hand, if I can reach some point from a core point with steps that are less than epsilon each, then it is a reachable point. This is medium density. They lie, we assume that they lie in the medium density region. All the points that for which there is no neighbor within the epsilon radius, that is an outlier, low density. Okay. Now what is a cluster? Cluster is basically set of core points and their reachable points that are within an epsilon distance of either another core point or another reachable point. So we could have a bunch of points here and we could have a bunch of points in that are somewhere else. Let us go back to that example that we had earlier. So here these core points, so if I draw a circle of radius epsilon around each of these points, if I take any of these, so let us say this is a core point. What makes it a core point is because if I draw a radius of epsilon, I will get more than min points, more than equal to min points within the radius epsilon. Now if I look at a reachable point, I do not have, let us say, 2 points within an epsilon radius, but there is a path that connects it to the core point by hopping over other reachable points or by hopping over the core points. Okay. So this hopping behavior lets me reach there, but if I draw an epsilon radius around this point, then there is no other point in the vicinity. So these are all outlier points. Similar type of behavior, similar type of analysis I can do here on the other cluster. So all these points are somehow related to each other through a hop of epsilon each, and they have at least one core point, and all these are related to each other through a hop of epsilon each, and they have at least one core point. So these are the two different clusters. So the number of clusters is not defined, only how much can I hop and how many points I need in the vicinity to form a core point. Only those two hyperparameters are defined, and the number of clusters reveals itself based on these. Okay. So these are our hyperparameters. The number of clusters is not our hyperparameter. Now what happens if I increase m? If I increase m, I will make the criteria for a core point to be more stringent and I will have fewer core points. What happens if I increase epsilon? I make the criteria for reachability to be more to be looser, and I will probably have merging of clusters if I increase epsilon. Okay. So these are to be kept in mind when you are looking at DB scan. So now the question arises is what is a good m and what is a good epsilon. So some of that will come from data exploration, okay, and from data visualization and understanding how many dimensions you are dealing with. If you have a very high dimensional space, again this distance, although we have this epsilon tolerance over distance, the distance being Euclidean doesn't help in when you have a lot of dimensions to play with. But be that as it may, we use that as a criteria for clustering. Okay. So here is a complete algorithm in a crude sense. There are ways to make it more efficient that we will not get into, but the core algorithm is like this, that for each point, so this is the first phase where we are trying to form the sort of like adjacency matrix, adjacency discovery. What does this mean? That we are trying to find between all pairs of points. If you have n points, then n choose 2 points, pairs of points. We are trying to find which points are adjacent to each other, which means that which points are within a radius of epsilon of each other, and we are trying to count the number of neighbors of every point. So we are trying to form sort of a graph. So basically what we are saying is that if you have points like these and then you have another set of points that are like this, Okay. So any point that is within a radius of epsilon with each other will share an edge on a graph. What is an edge on a graph? Edge is basically a line that is represented between two pairs of points, and it is connected only if the edge exists between those 2 points. So what is special about these lines? All these lines are less than epsilon. Okay, all these red lines are less than epsilon. So we are trying to do this adjacency discovery on the data points. So for each sample xi, okay, and each other sample xj, we can probably make it more efficient, but let's start with this. Mark j as a neighbor of I, okay, if distance between I and j is less than epsilon. All right. Increment the number of neighbors ni of xi. Okay, so we are also counting the degree of each vertex. What is degree of each vertex? How many other vertices it is connected to, how many neighbors it has. All right. So this is the adjacency discovery phase, and then we will do the marking phase. So for each sample xi, if the number of neighbors is greater than equal to m, that means the degree is greater than equal to m, then mark it as a core point. If the number of neighbors is greater than 0, okay, so this would be else if, and this will be else if, then mark it as reachable. Okay. So any core point that has degree greater than 0, any non-core point that has degree greater than 0 is going to be a reachable point. Okay. And all that are left which are not reachable, okay, where the degree is 0, these are outlier points. Right. Once we have done that, the third phase is that we will find out all the clusters. So this is marking points, this is the marking phase, and the third phase is the cluster discovery. In the third phase, we will look at each sample xi. All right. First, we will mark all points as not belonging to any cluster. That is not written here. Mark all points as unclustered. All right. Then for each point xi, okay, if it is a core point, and it is unclustered, then mark all its connected samples. Okay, so we will do a depth first search or a breadth first search. We will traverse everything that is reachable from that point and mark them as part of the same cluster. So for example, let us say we discover, we start with this core point, then we will do a breadth first search and we will find all these points, and then we will iteratively do breadth first search, okay, and based on that we will mark all these points. Now because they are all reachable from this point, these belong to one cluster. So now if I go to another point and it is already clustered, then it is not unclustered, so I will skip that. I will keep skipping that until I find a core point in the other cluster that is yet to be discovered. In that cluster, now I will do a depth first or breadth first search, and based on that I find that this is the second cluster. Okay. So that is a crude way of describing how DB scan will work. Okay. So now comparing DB scan and k-means or fuzzy c-means, they are basically approaching clustering from two different ways. One, k-means and c-means are saying that we know the number of clusters and we assume that they are mostly equal size hyperspheres, right. So we have the underlying density of points is multimodal Gaussian, multimodal isotropic Gaussian, where each mode has the same is isotropic as well as has the same variance. On the other hand, DB scan is saying that no, let densities be anything, but let us have an assumption on what will be the how many points will be sampled from the high density regions, how tightly they will be sampled, and whether we will be able to discover the other points in the vicinity or not. only the edges of the clusters that are discovered through DB scan, those edges are roundish in shape, because ultimately we are still using Euclidean distance for the discovery of neighbors, for the adjacency discovery. Now what if we want to have the entire set of clusters from one cluster to n cluster, or from n cluster to one cluster, and then later on decide that somewhere between 1 and n lies the true number of clusters, okay, by after doing the clustering. So that is where hierarchical clustering comes in, where the hierarchy is from n to 1, okay. So n means every point is a singleton cluster, okay, and now we will iteratively merge clusters until there is only one cluster left, okay. So start with each cluster and merge. In each merge iterations, how many iterations will have? N iterations, where n is the number of points for each cluster, and find every other cluster, compute inter-cluster distance and merge the two closest clusters. That is basically what we are doing in each iteration. So within each iteration we are just merging two clusters. So in the end we are going from n to 1 clusters. An example of this would be, let's look at one dimension. So let's say you have only x1, okay. In x1 you have points that are like this, alright. Let's take this example. So now let's see how we can merge these 2 points. So here let's say this is our merging distance, and this is x1. Okay. So when your merging distance is 0, right, then no cluster will be merged, all clusters will be separate, okay. So for each cluster we basically start a line going upward when the distance goes from 0 to some other distance. So when this distance between two closest points, right, when we reach that from 0 to that distance, this is the min distance, then these two points will merge, and we will draw that with a horizontal line. Meanwhile these 2 points have not yet merged, they will keep going, okay. So after some time the two nearest points, they will merge, but these two will not merge, these two will continue and these will continue, then these two will merge and this will continue, okay. And then we will reach a distance where these two will merge and then we will continue, and after a long time these two will merge, okay, and it will continue, and after a long time these two will merge, okay. And then if we keep increasing the distance threshold, then basically after that we have one cluster. So here we had n clusters, here we have one cluster, okay. Here we have n clusters when the distance is 0, and we have one cluster when the distance is infinite, okay. So now the cluster can have an infinite size and it contains all the points, okay. So here this kind of a diagram is called a dendrogram, okay. And this dendrogram is sort of like a tree, where at each level we see, if I draw a horizontal line at any level, so let's take another color. So if I draw a horizontal line at any level, so this is my clustering distance criteria, okay, and the number of cuts that I have, basically those tell me the number of clusters that I have with that criteria. So it gives me a continuous criteria that gives me different number of clusters. Here I have 2 clusters, here I have 2 clusters, here I have 3 clusters, right, and below that I have 4 clusters, etc., up to n clusters when I go to distance equal to 0. So now this gives me a choice of where I want to, how many number of clusters I want, and where I want to cut the dendrogram, okay, which horizontal line I can use to cut the dendrogram. Now what we want to see here is that what is a good number of clusters. So where should I cut the dendrogram? A heuristic could be that wherever you have the maximum vertical tolerance before the next cluster merge, between the next and the previous cluster merge, okay. So that could be the point where we cut the dendrogram. Okay. Maybe this is not like this, maybe this is going to be between this and this. So this is the tolerance that we have. So wherever you see a large vertical distance, that's a good indication of where to cut the dendrogram. Not always so, but that could be one criteria. Other criteria could be that we also take into account how many points are being merged and so forth. Okay. So there are a couple of things that emerge here, that whenever we are looking at the smallest possible clusters, which is n clusters, each point being in its own cluster, then within that cluster the variance of the points is 0. And whenever we are looking at the single cluster where all points are belonging to one cluster, the variance of the point is same as the variance of the entire data. Okay. So variance of the data, entire data, and variance of the cluster. Okay. So these are two different metrics to keep in mind. We will look at their interplay in deciding the number of clusters. So before that, let us look at how we will merge the clusters. So there are different ways of merging the clusters based on the distance. So that distance, that was the vertical axis of the dendrogram, we want to see what is the criteria for that. So there are three broad criteria. We can have other kinds of criteria also. One is single linkage, the other is complete linkage, and then the third is centroid distance. So single linkage is based on minimum distance between two clusters, between any 2 points of two different clusters. Maximum is based on the maximum distance, and average is based on the distance between the centroids. So for example, if you have this cluster and you have this cluster, okay, and you have a third cluster, okay. So now let us say that we have these the following cluster memberships. So this is one cluster, this is another cluster, and this is the third cluster. Okay. So now we want to decide which of the two from these three have to be merged. Okay. So the minimum linkage will look at minimum distance between clusters. So the closest points between any two clusters. So here it is going to be between this point and this point, this point and this point, and let us say between this point and this point. Okay. So between the three green arrows, whichever is the minimum, that will represent the merging. Okay. So that is minimum. On the other hand, if we are looking at maximum linkage, then we will look at the maximum distance, so which could be, for example, between these 2 points, okay, between these 2 points and between like these 2 points. So between the blue arrows, assume that these arrows are not curved but straight lines, the ones that represent the minimum, those two will be merged. So that is maximum linkage. And the third criteria would be that we are looking at the centroid, where we first find these centroids. So we have this centroid, let us use a brighter color, orange, how about orange. So let us look at this point, we look at this point, and we look at this point, and now we are looking at the interdistance between the orange clusters or cluster centers. Okay. So that is the centroid based distance. So depending on which criteria you use for merging, your order of merging could be different. Okay. So depending on the application, you would either use a single linkage or a complete linkage or a centroid distance. Alright. And these distances, in general we are talking about distances between xi and xj, or xi and cj, or xi and μj, right. So xi and μj, or the centroid, etc. This distance need not always be a centroid. Okay. It can, this need not always be a Euclidean distance. What you can have is Euclidean distance. You can also have Mahana-Lobis distance. Okay. You can also have some sort of a distance metric which is neither of the two. So for example, it could be based on inverse of similarity. Similarity is computed by a Siamese neural network or something along those lines. So it could be some dissimilarity metric. So it could be actually any pairwise distance, as long as we can compute something that is pairwise, it will work for many of these clustering algorithms with slight modifications. So it need not always be Euclidean distance. We can even weigh some of the variables to be large distances versus small distances and so forth. Okay. So now let's look at some clustering criteria. Because it's an unsupervised learning, right? We are always wondering about whether we chose the hyperparameters to be correct. So for example, in k-means and fuzzy c-means, did we choose the k or the c correct? In dbScan, did we choose the min distance and the min number of points m and the distance radius epsilon to be correct, and so forth. There are many different ways of measuring whether a clustering criteria is good. Okay. In general, they are based on looking at whether points that belong to one cluster, they are more similar to their own cluster, the members of the same cluster, compared to the distance from other points that are outside the cluster. So that is the general criteria. We will look at two different ways of looking at it. One is the elbow criteria, the other is Davis-Bordin criteria. So in elbow method, we are looking at the percent or the proportion of variance that is explained by the clustering. So we have something like number of clusters. All right. And this will range from 1 and it can go up to n. Okay. And on the y axis we have variance explained. Okay. So if we have n different clusters, right, they will explain all the variance that there is. And if we have one cluster, then probably it will not explain any variance. So we will have a curve that will go like so, and somewhere it will have an elbow, and that elbow represents good number of clusters. Okay. Now this elbow itself is subjective. Okay. Whether it really represents something natural, a natural cut, we don't know. It could be a point of inflection, it could be something like at this point the rise is only 5% more, the 95% rise has already taken place. So a lot of these are still subjective criteria, but this visualization can help in deciding the number of clusters. So what is variance explained, right? So basically what we are looking at is between group variance versus the total variance. Okay. And basically it could be for example total variance minus the average or max variance within the cluster, right. So if we look at the total variance of points and we look at total variance of one cluster, we take their difference, we will get zero variance, we will get a zero difference, right, because there is only one cluster. The total variance of the data points, okay, is same as the variance of that single cluster, so we will get 0. On the other hand, so let us say these are the points and these are two different points, so two different sets of points. If we look at this set as well as this set, right, the total variance would be proportional to, let us say, the radius of this circle. Now from that, if I subtract either this average radius or the max of these radii, I will get some point which is there for two clusters. Okay. That difference would be somewhere here. and let us say that is the elbow point, that looks like a natural cut, and that would be the number of clusters that I have. So that is heuristic criteria, heuristic method to look at this using the elbow method. I encourage you to look at something similar called silhouette method. Okay. Now let us look at a slightly more mathematical index, mathematically well defined index, which is the Davis-Bode index. So here we are looking at two things, right. So instead of having that elbow, we are going to now convert that into a ratio so that we get a minimum. Okay. So basically what we are trying to minimize is the ratio of intra-cluster versus inter-cluster variation. Let us unpack this for a bit. So we want minimum variance within the cluster, so that we want points within the points in a cluster should be similar to each other. Relative to points outside the cluster. Okay. So for this we will look at the variance in cluster I and variance in cluster J. We will take their average, or we will take their sum, and we will take its ratio with, if we take all the points together for the two clusters, what is the variance. Okay, we will take that ratio, alright, and or we can take the distance between their centroids. Mij could be distance between the centroids of cluster I and cluster J, or it could be the variance of cluster I and cluster J points taken together. One is computationally more efficient, whereas the other could have nicer mathematical properties. So we will take these two ratios, and we will take the maximum of that over all other possible clusters for the ith cluster. So I and J are clusters, cluster indices. Okay. And we will take that average over all clusters, and we want to minimize it. So basically your this will be your DB index, and this will be your number of clusters. And basically let us say if we start with one cluster, we want this to go down somewhere and then go up somewhere. So this will be the ideal number of clusters, but in realistic data this will be somewhat noisy, and it may not always give you a global minima. So it's not a foolproof method, but we still want to we can use this method, and similarly there are other methods that also give us similar answers. Now the challenge here is to keep in mind that no criteria is perfect, number one, and number two is that whenever we are doing this, make sure that the index that you are using it has some sort of normalization for number of clusters, because we are looking at an average here, there is a built-in normalization here. So now let us look at how does transformation of variables can have an impact on clustering, right. So let us look at a set of data points that we want to cluster. Okay. So this is my x1 axis and this is my x2 direction. Now for some reason, if instead of x1 I use, let us say, x1 by 5, right. If I use x1 by 5, then my new x1 hat is equal to x1 by 5. So I am going to stretch my axis. So this same number of points are going to be stretched. In one direction and not in the other direction. So what could have been a clustering like this, now becomes a clustering like this. Okay. So the scale of the variables is very important. Okay. So a good practice is to normalize each dimension separately so that it has unit variance, for example. Okay. The other possibility is that you also want to look at whether the scale of one variable should be converted to a log transform or to a power transform. So for example, if my x1 is revenue per customer, okay, we know that revenue per customer distribution is going to be some sort of a heavy tail distribution, sorry, it's going to be a skewed distribution. What that means is there are few customers that spend a lot of money, and there are a lot of customers that spend some sort of medium sort of money, but that's not right in the middle of the range. There is a tail skew towards the right, right. So this tail skew towards the right, it violates the assumption of isotropic in both directions of x1, right. So the hyperspheres that we had in k-means, they were isotropic, but this violates that assumption. Whereas if we if we take the log transform, we are going to compress the higher values and it might transform into something that looks more like a Gaussian. Okay. So taking the transforms of variables is quite important, okay, in thinking about whether I should be applying clustering to it right away, or whether it should be on the transform variable. So depending on the application, you want to take the right kind of transform. Okay, so with this we are coming towards the end of the discussion on clustering. There are just two prompts that I will have here, that there are advanced topics in clustering. One of them is basically, like I mentioned, clustering is finding modes, different modes of a underlying probability distribution, and if we assume the underlying probability distribution to be a mixture of Gaussians where the variance of the Gaussians is different, then we can actually do a Gaussian mixture modeling, which I will talk about later in the course, using something called expectation maximization algorithm. So that we will cover later, but I do encourage you to look at another type of clustering, advanced clustering techniques rather, it's a set of techniques which is called spectral clustering. I'll just give you a brief idea of what is spectral clustering. Basically what we are looking at is, let's say we have data points x1, x2 all the way up to xn, and we have dimension d1, so we have dimension 1, or let's call it, yeah, like we had genes g1 up to gd, d dimensions here, right. So if we look at one particular sample, one particular patient for example with different gene profiles, we can see that that if we look at them, if we find those that are similar to each other and they form a cluster, and others that form another cluster and so forth, how we can now transform this is to plot something called a similarity matrix. So the size of the similarity matrix is n by n, so this is n by n, and basically what we have at each point is similarity of ith point, ith sample with the jth sample. Okay. So the similarity is going to be high on the diagonal and it is going to be low off the diagonal. Okay. So now with this we can rearrange the rows and columns of this similarity matrix such that it has a block structure. We have a block where we have bunch of low values, then we have another block that has bunch of low values, and then we have another block that is a bunch of low values. So what all we are doing is we are permuting rows and columns so that the rows that appear together and the columns that appear together, they belong to one cluster, and these rows that appear in this block, they belong to one cluster, and so forth. What is special about these blocks, that these are low values, not just on the diagonal, on diagonal will have zero value, sorry, these are high values for similarity, not just on the diagonal, because on the diagonal we will have the maximum similarity, these are high values. Everywhere else we have low values. So this block diagonal structure is a way to visualize these visualize clustering of different samples, and the way we get this is that if we look at each of these rows, right, those that are similar to two samples that are similar to each other are also their similarity pattern is also similar to other rows within the same block. Okay. So the discovery of that is dependent on eigenvalue analysis of this similarity matrix. We can have a similarity metric or we can have a distance metric, and the eigen analysis would just change in how you look at the highest eigenvalues versus the lowest eigenvalues, but that is basically the whole idea. So what we do is we will get these similarity matrices, and based on these similarity matrices, after that we will do an eigen analysis, and based on the eigenvalues that we get, we will be able to find out different modes of variation within the same matrix, and that basically gives rise to a whole bunch of techniques called spectral clustering, which I will not get into here, but it is a very interesting topic should you want to explore more. So then there are methods such as graph cut, where you look at these matrices, you form a graph between all the sample points, where having an edge between two samples means that they are similar. If there is no edge, that means they are not similar, and then what we are trying to do is we are trying to cut that graph with minimal number of cuts, and that will give us the clusters that we have for the data points. So these are ways where you can go beyond the Euclidean space, beyond just looking at Euclidean distances, to work with other similarity metrics to cluster points. Okay. With this I come to an end of this topic of clustering. Thank you.